One of the most informative and transformative technology is the internet, which has been around for some decades. For all these decades, it's been known as a product for people. But things are changing so fast right now, it's not only about connecting people, but also connecting things. Things that can communicate with each other, share information, and make our life beautiful. Such things with internet can be called smart objects or the Internet of Things. IoT is the main concern of the presentation that I'm about to present. The title of our paper is Service-Based Fog Computing Model for IoT. This is Sayed Erfan Arefin, one of the co-authors of this paper. I'm from Brak University, Bangladesh. By now, all of you have heard the term Internet of Things. It's a really interesting thing. But what does this actually mean? IoT is a revolutionary technology of mobile, home, or things that are connected to the internet, integrating greater compute capabilities and using analytics and other cloud computing services to gather data and extract information from them. Billions of devices are now connected to the internet, and soon hundreds of billions of devices are going to be connected to the internet. As the devices gets connected to the internet and starts talking to each other and starts sharing information, they are creating intelligent systems, intelligent system of systems. And when they collect and share data and analyze it over the cloud, they can transform our life and make it better in countless ways. They can be used for medical purposes or for producing goods faster and cheaper ways, making shopping more enjoyable or optimizing energy generation, consumption, and distribution. As an emerging technology, the number of devices connected to the internet is increasing. IoT communicates with the cloud directly. In case of large-scale usage, even cloud cannot handle this amount of data stream, constantly asking for different services. In order to resolve latency, network inaccessibility, rising cost, and data security concerns, a new distributed technology came to being. That is fog computing. Here, compute, communication, control, storage, decision-making, etc. are done closer to the place where data is originated. These edge computing concept solves several problems. Our proposed infrastructure uses fog nodes as middleware. The middleware of our proposed infrastructure uses service-oriented architecture to minimize the usage of services even more. Service-oriented architecture is more of a service-based model where each and every service is composed using some other services. You can use the same service to compose different services by arranging them differently or using them differently. In our model, the middleware, we use two types of SOA. One is just the SOA, the service-oriented architecture, and another one is the agent-based SOA. Now, I'm going to explain a simple simulation of our proposed infrastructure so that we can have a better understanding how this infrastructure will work. There are 4 layers, as you can see. At the bottom, we have the IoT devices. At the second layer, we've got the middleware, the SOA. And at the third layer, we have the agent-based SOA. And at the top, we've got the cloud service. So, when a device requests for some kind of a service, it gets through the second layer, the third layer, and from the cloud based on if its necessity. So let's say the device 1 here is going to ask for service A, and it will not be found in the second layer initially or in the third layer. It's going to find the service from the cloud, and it's going to return to that device. Now, here is a thing that we can observe. Once the service A is returned, the service A has an instance in the second layer. So when the second device asks for service A again, it doesn't go through the third or the fourth layer. It simply returns it from the second layer. And now, let's say the third device here is going to request service B. Let's assume service B is composed of 3 components. Among those 3 components, 2 components are common with service A, and those 2 components are available in the third layer. So when this third device is going to ask for service B, it is going to find those 2 common components from the third layer and only going to ask for the missing component to the cloud. And when that missing component is returned, it will compose service B and return it to the third device. And when the fourth device is going to ask for the same thing, service B, it doesn't have to go through all the composition thing. It will simply return it from the third layer. And this is how our infrastructure will work. Now I'm going to explain how we tested out our infrastructure. It's really hard for us to test this infrastructure out in real life. So what we did here is we tested our infrastructure in Microsoft Azure, a cloud platform offered by Microsoft. So we use data centers here, which are situated in different regions. We created virtual machines inside those data centers, and basically these virtual machines are virtually created, but they exist in different regions physically. We use their public IP to access them, and these VMs are treated as fog nodes and IoT devices. This means we recreated the scenario that is needed to test our infrastructure using virtual machines in different regions. This is the graph that we have generated from the network monitor of those VMs. As we can see, the traditional model graph consumes more data depending on the requests made by the IoT devices. But for the same amount of requests made by the IoT devices, our fog model requires less data consumption. This brings out several benefits. This helps building geo-redundant replicable local backup, low data consumption, proper utilization of bandwidth and traffic, reduced latency, and request redundancy. Here is a graph of our infrastructure's data consumption. Here you can see in the x-axis we have the number of requests, and in the y-axis we have data consumption. You can see the number of when the number of requests increases, the data consumption goes down, and it follows more of a logarithmic pattern here. This is how we can say that our model is better than the traditional model. The traditional model will follow a linear line. This is the end of my presentation. Thank you.